Welcome back. Our next speaker is Józef Przytycki from the University of Washington, and he will tell us about the Kauffman and Dubrovnik polynomials and the cubic skein modules and beyond.
Thank you very much, and it's a great pleasure to give talk in Warsaw after many years. I did my master degree here in 1977, and we started our adventures with Humphrey polynomial in 1977 master degree, 1984, and there's here my co-author, Paweł Traczyk, so it's great that he came, and then maybe I will tell more about history and my, my adventures. But really the topic is continuation of kind of, or maybe parallel to Ria talk. She introduced various skein modules and concentrate on Kauffman bracket skein module. I will talk mostly about cubic skein module. This is our project with many students or former students. And we are at the very beginning of the journey. We don't know much, so some results are kind of basic, essentially the same as Ria was talking about. For example, that there is functor from three-dimensional manifold with embedding into modules. This is kind of universal, so we can, of course, analyze skein module piece by piece, try to analyze piece by piece, etc. I will concentrate on skein module. So first, of course, let me repeat what is the idea of skein module. So general idea that was that if you take n-dimensional manifold and some submanifold embedded, maybe classical codimension 2, or maybe some codimension 1 sometimes, or higher codimension. However, really skein module will develop better for three-dimensional manifolds, slightly on four-dimensional manifolds. Here one should mention the recent papers by Manolescu with his co-authors about lasagna skein module, which for him is used to construct exotic structure on four-dimensional manifolds. But I'm working mostly here when this, so skein modules I think Ria was mentioning, so skein modules from my point of view is 1987, I know April. So I was mostly defining them for three-dimensional manifolds and links, but I was mentioning that there's one possibility, then I talked about one possibility of surfaces in four-dimensional spaces, and you can, definitions usually is easy to give. For skein module, it's important not only to give definition, and beauty of this is that definition always works, but to be able at least to compute for some simple manifolds, like S3 or Sn in more general case. Even for cubic skein module, we don't know answer for S3. So what is general idea is that we have some pieces of the usually local, however not always, usually dn in n-dimensional manifold D3 here, and we put some linear combination. So we take links, we take some ring, and we take formal linear combinations of links. So again, this idea to understand complicated object by taking the linear combinations and dividing by some submodules, some subgroups. So the object became simpler. It's pretty old. I think start with Dedekind in 19th century. In knot theory, maybe you say the pioneer was Alexander or maybe Conway, but these are kind of non-clear things, but in algebraic geometry, I think Dedekind. Anyway, so we take linear combination of some pieces and divide our free module over all links in our manifold. Let's say three manifold here. So we take linear combination of all links and divide by relation and up to our imagination, which relations we take. So, as I said, you can put many relations, but one has to be able to compute. So one of the objects which I defined in this first paper in 1987 was what Ria was saying, that we just assume that related objects are just twists in one place. So, as she wrote, we take links in manifold, one should stress immediately we assume that it's ambient, up to ambient isotopy, or how physicists in 19th century will say up to natural deformation. So this is the reason that there's no problem later with definitions. Already links are up to ambient isotopy. Then we take the linear combination and define by relation. So this was, which Ria described, this first relation I taught above, Humphrey, Kauffman, Brackett, and Kauffman and Dubrovnik. So this was more or less like this. She drew pictures. So these are local pictures. Plus, we put n objects, bn minus 1, with n minus 1 twist, half twists, plus we allow vertical thing. So this is relation after the quotient, this is 0. And then, and this is kind of gradual we came to this. When I first defined scale modules, I was hesitating. Luke Kauffman was, because he was working in S3 for Kauffman bracket, you may know, prefer to say about right numbers, number of positive crossing minus negative, but it doesn't work if you go outside at least rational homotopy spheres. So he had this idea, but he didn't kind of stress this, that another possibility is to work with framings. So I think Ria was drawing this, but I think chalk is perfect to draw. So in standard knot theory, when you have not ribbons but just knots, this is the same as trivial thing. But if we just have a ribbon and you make it straight, it will look like this. It will really, framing will be twisted. So it is natural not to put them there equal, but put some variable. And this I will always do, some variable corresponding to twists. You can say that you lose some information, but don't lose that much. At least comparing later with scale. So this will do always. This is essentially what Kauffman is doing when he defined his Kauffman bracket. Maybe more about this. But what was this nth scale module, which, as Ria said, was denoted as n infinity? Rather naive notation, but I should stress this was the first paper, the first thought. So I was describing in this picture how many horizontal pictures is and vertical. Vertical was then infinity. Now people rotate this very often. So anyway, so this is just we divide formal linear combination of, if B infinity is not 0, then there's no natural orientation here. Of course, you can still do some tricks, but generally there's no natural orientation. So if B infinity is not 0, then we put unoriented links. So this is this divided by our relations from above. So this is kind of why it is good, because there's general definition. Definition already is giving result. The object we get, we can say, is invariant of three-dimensional manifold without any thinking by definition, and every link is representing some element of this module. So as I was saying, for example, Kauffman bracket and S3, thus the module is the same as link. Of course, we should say that these are elements of B0, B1, B2, Bn minus 1, and A are elements of our link. To be able to make any calculation is useful to assume, and we always assume that B0 and Bn minus 1 are invertible. Otherwise, of course, still you have nice module, and maybe it is even interesting, some zero divisors, some annihilators, but it is not convenient to work, so we'll assume that B0, Bn minus 1 invertible. I will show one long calculation with them invertible. Then A for sure should be invertible, because we can rotate framing forward and back, so should be going one direction should be A, another direction should be A inverse. So maybe let me write this. Invertible. these three elements are invertible in the ring, and essentially this is what is needed to do at least some basic calculations. Anyway, I have in mind already cubic, something only one step above Humphrey and Kauffman and the Dubrovnik version. I will tell about this later. So now just general things. So B infinity. So really there are two important cases. B infinity is 0. Then we have two options, which I think we'll discuss when I was talking. Either we can still work with unoriented rings, or because we can put orientation, because if we have orientation, then it can have orientation. If we forget about this, then let's say parallel orientation, then we can work with this skein module, and as she said, if n is equal to 2, and n is equal to 3, when it is quadratic skein module, then in oriented version with B infinity 0, we had Humphrey polynomial. In fact, we have no restriction on coefficients. And if B infinity is not 0, then we'll assume invertible. Usually, then it is either Kauffman polynomial of two variables or Dubrovnik, which is a small version of this. So I will assume nothing in between. The second version will be B infinity invertible. Most of the study recently we did was for B infinity invertible. B infinity equals 0. I was studying with my student many years ago, so basic things we did. And then always you try to guess really what are these coefficients. So let's see one thing what we can do in general before I will go to lower degree. So, and this is typical how we approach this from the very beginning when nothing is known. When nothing is known, consider what we call denominator of this picture. This is one of the notation of Conway. Conway was very innovative in terminology, but this part of terminology stays. If we close the tangles, or maybe I should write definition, if you have two tangles, meaning something like this, decorated inside by some diagram, then I will use color. Then if you close this like this is called denominator. If you close the one, it is, I call this half denominator, but denominator. Denominator of tangle. So you can guess that numerator will be closing on the top. There are two states only, without crossing. So denominator, so here the nose is T. Okay, so we can, first identity we get is by considering denominator of this equation. Because once more I should stress, we are saying that really this is local picture. We can imagine that outside there's some feeling, not necessarily close, but there's outside, but what is important is that outside is the same for every picture. We modify, we have linear relation only on these blocks. So let's do this calculation. Maybe I will do this calculation already with some notation. Maybe why notation? Let's do pictures. So it is B0 plus B1, maybe I will not draw too many, plus Bn minus 1. Then we have n minus 1. Plus B infinity, like this, is equal to 0. Okay, now let's take denominator. So, this is trivial knot. Let's call this T for simplicity. What is this? We can do first Rademeister move, but we should check whether we multiply by A or by A inverse. I will use this convention. How to quickly decide, at least how I quickly would decide, that I will put orientation. It does not depend on orientation, but orientation. and see whether it is in our convention positive. Not, this is positive. So here I suspect it will be negative. Yeah, this is the opposite. So this will give A inverse T. And etc., etc. So because it was from n minus 1, it will be A to 1 minus n. Not here, here. A to 1 minus n T. So we got identity. And here we get two components. So in such a way, as long as B infinity is invertible, we can compute really T, assuming that there is no universal annihilators. Okay, so what this equality is giving exact as I wrote, it is B0 plus B1 A inverse plus B2 A2 minus 2 plus Bn minus 1 to power 1 minus n plus, here is just T square maybe, but T times T is equal to 0. As I said, I don't like this annihilator, so I will have just a relation that this is equal to 0. Almost follows. So this allows T be infinity. So this allows us to compute T if B infinity is invertible. That is 1 minus B infinity, and in parentheses will be what was here, B0 plus A inverse B1 plus B plus A to 1 minus n, B n minus 1. So yes, so as long as B infinity is invertible in this universal thing, we can compute T. Maybe one more about general case, what we can say, just ideologically. What you can think that what we are doing here. You can think, I assume that these are invertible in particular. You can think that for a specific case when everything between is 0, we are just going from parallel copies to here n minus 1 copies. So generally it is useful to think that our skein relation, n skein relation, is deformation of one move. So we have a name for this. I will call this k, so not to mix with n. So if we have such an operation, here is n minus n, or maybe k, I said, k half twists, positive half twist, half twists. So here you have 0. In our notation, this will be, say, d0, and here will be dk. So if we have such a move, I call this k move. And we can analyze, say, in S3, but everywhere, links up to these moves. This move is not topological. This is changing topology. So many links you can simplify. So n move, k move, and if L1 and L2 are related by k moves, we say that they are k move equivalent. So that's definition. So in old time, when I was analyzing this first time, my goal was to see how then classical polynomial, Alexander polynomial, but then Jones polynomial and Humphrey polynomial and Kauffman polynomials are changed by such a move. And this gives nice result in this classical case. So today I would like to make one long calculation how our cubic scale model changed in this move. This is, I should say, high school calculation, but somehow always I have trouble with this calculation. So I will show you how trivial you can do on the level of probably middle school in Poland, high school in America. So, okay. So anyway, Ideologically, what I wanted to say is that studying n-moves is really analyzing deformation of n-1, because we end on n-1. So this deformation of something we can study first. And I can add immediately that first of all, what is 2-move? 2-move is just crossing change. So at least in S3, it's just reducing links up to homotopy, or you can say in S3 that every link is equivalent to trivial link of the same number of components. Because 2-move is going from this to this. But if you can go from this to this, it's the same as going from let's say negative crossing to positive crossing. So 2-move is good. Quadratic scale modular deformation of 2 moves, but this reason that are relatively easy. Because we know how to reach from any link to trivial link, and then you have to analyze very carefully this deformation. But it works. So now what about 3-move? I think I will erase my apart. So for cubic skein module, so maybe I should stress once more, for n equal to, what will be n? 4, yeah? N equal 4 is cubic skein module. If you have this relation. So yes, so like if polynomial have k coefficient, so it is of degree k minus 1. So 4 coefficients, degree 3 cubic. Okay, so I was supposed to do here. So 3-move. And when I started the topic, I learned that already Nakanishi have conjecture, which is kind of analog of this 2-move, that every link in S3 can be reduced to trivial link by 3 moves. But this was then conjecture. I write it still named Montesinos Nakanishi, but really Montesinos nothing have to do with the conjecture. He was analyzing 3 moves from the point of view of threefold branch covers. Anyway, I will still write Montesinos Nakanishi. So this is every link in S3 can be reduced to a trivial link by 3 moves. Then I had hope that at least in S3, in general cubic relation, every link is linear combination of trivial links. This was the hope when I started analyzing cubic skein modules long time ago. So let's do now to k equal n equal 4 cubic. So for cubic, anyway, for B infinity invertible, we know we can compute T. We can compute what happens when we have trivial component. Okay. So let's write it again. So we have, let me write from B3 plus B2. I'm writing backward, but plus B1. Plus B0 plus B infinity. So this will be after quotient 0. So it's cubic skein reduction. So the first conjecture, natural I made that every link in S3 can be written as linear combination of trivial links. So maybe before I go further, let's see example how it works. So trefoil is the easiest example. Easiest non-trivial example. This is trefoil. I draw trefoil so we can easily apply tree move or inverse of tree move. It's equivalence relation. So after tree move or minus tree move, every crossing is eliminated. So I get this. This is a good example because it's showing, which is of course natural, that conjecture was that every link can be reduced to trivial link by tree moves, but number of components is not preserved by our move. So here trefoil is equivalent to trivial link of two components. And links of different number of components are not equivalent. This is very easy because Fox coloring is.
Oh, sorry, this is my mistake.
Okay, half, yeah?
Okay, very good.
So yes, so various number of components, and this can be, but the different component can be distinguished by easy invariance Fox tree coloring or something like this. So it's not big. But what happened is that this conjecture happened to be false. So this is conjecture, this is 1981. So 21 years later, if my student Dąbrowski, you can write this all nicely. I think it was maybe it was 2000 already. 2002, I think. That in 2002, we proved that conjecture is false. So, how to prove such things? So, we were trying to find some delicate invariants of tree moves or generally n moves. The standard invariant, I mean, some substitution in Jones, some substitution in Conway, they are not working very well. So what we found was you can analyze what we named Burnside group of a knot. So I will just write slogan. So first of all, conjecture is false. Hold. The method was Burnside group of a link or a knot. And for people who know, I will write definition. So we take our link, we take double branch cover. Like now it's very fashionable because we know what Chowanov homology is converging to Higald floor of double branch cover or something like this. So we take double branch cover with branching over L. We compute fundamental group. And finally, this world of Burnside came that we divide any world by, in our case, third power, generally nth power. But in our case, it's just third power. But it's not generated, but every element. Like in Burnside group, we take three group and we divide by n power. And what is good, that was already proven by Burnside, that for n equal 3, this group is finite. So we just use computer and check values examples. And it happened that already my student couldn't simplify one 5 braid. So this was contact example. The first we found was sigma 1, sigma 2, sigma 3, sigma 4. It should be sigma 4. It should be twice full twist. So it would be power 10. So rather nice thing. So maybe here as well. Why this example we're checking? So there was a student called Chichen, and he wanted to do some research. So there's another very tell anecdote, that's it. Namely, there was a paper by Coxeter from 1957. And what Coxeter did in this paper, he was analyzing braids Bn, and dividing by powers, but this time of generators, not all, but powers of generators, let's say, to k power. And in this paper, he analyzed when this group is finite and when it is infinite. And he found, I will write it in a nice way, that it is finite if and only if 1 over n plus 1 over k plus 1 half is greater than 1. So, except the case when you have two braid, there is finite number of possibilities. In particular, from this follows that B5 divided by sigma 3, sigma I to third power, is finite. It has, Coxeter show a few thousand elements. But I told him you have only first, and why divided by third power? This is really tree move, even oriented tree move, but it's tree move. So already for 5 braids, this is very good first step. You have finite number of elements to check. And he did this, he did for 3 braids, 4 braids, and finally for 5 braids. He couldn't simplify this element. So, as you can guess, with Mietek-Dąbrowski, we first example, non-trivial example on which we tried Bell-side groups was exactly this thing. And yes, Bell-side group have 3 million elements, and our group for this braid was smaller. So, conjecture is false. For cubic skein module, it makes story much more difficult, because it means that if you have, for sure, for some parameters at least, if you have cubic skein module of S3, then it is not generated by trivial links. In particular, you can add to generators this plate. You can ask if you like to work on this, what is open here. In fact, this by 3 moves is not so difficult to reduce to 20 crossings. But conjecture, and some people claim they check, but there's no record of this, that this 20 crossing braid or not, or link, it is link of 5 components. This 20 crossing is the smallest. The Montesinos-Nakanishi conjecture holds for links up to 19 crossings. This is something with strong computer one can now check, because I think knots at least are classified up to 19 crossings. Of course, you have to do 3 moves, and you don't know how far you have to go. Maybe to simplify something, you have to go very far. Even for a small knot, you know that some knots with 8 crossings, you have to go to 10 to simplify them. But very likely, it was possible to do with a computer. Anyway, this is the first model. Of course, you can say, oh, is it always true? I mean, more or less. But for sure, if B1, B2, I mean, in our model, B1 and B2 are 0 and B infinity says 0, we just ignore this, then you cannot simplify. So this is one thing for scale models. So I think what we know more. We did various tries with our calculation. So let me show one calculation before I will finish with long calculation, but boring. Okay, this I can erase. Now we will, maybe this Coxeter. So this paper of Coxeter still is almost unknown, because it was not in abstract, now it is not still in MathXCnet. Somehow it was missed, Coxeter paper. So you cannot find just searching in MathXCnet. Of course, now I'm sure that people put on the web this paper. But it's very, very nice paper, and Coxeter initially thought that it's not a big deal. People who know can, I erase this inequality, but that it has something to do with triangle groups, because equality looks like triangle groups, but 1, 2 is artificially already given, which makes sense. So this is about Coxeter paper. Now some calculation. Probably I don't need this. So it is tempting, so choice of the ring. It is tempting to just think that we can work with general ring. We decide that B0 is invertible, B1 arbitral, B2 arbitral, B3 invertible, B infinity, there are two cases, but let's say B infinity is invertible, plus minus 1. And finally, A invertible. That maybe we can work just with this ring of polynomials. We don't work in this case with T which describes trivial link, because already I showed that trivial link in this case can be computed from the rest. So it's tempting to work with this polynomial. But you can ask, is really this polynomial not too big? For sure must be more relations. We know that for smaller, for Kauffman bracket, and for Kauffman and Dubrovnik polynomial, whatever they are, we need to put some substitution to have invariant under Rademeister. But on the other hand, Humphrey polynomial has no restriction. So this is what I can remind this with Pavel when we start working. I wrote Alexander polynomial, John's polynomial, and said probably wise people already were thinking that there is no more. But Pavel told me just see if there is no, if there is limitation, you should find some idea by which we have to divide this polynomial. It happened that for Humphrey there was no restrictions. But when you start to calculating, you see that there is no restriction. Okay, so what here? So let's try. What I mean by let's try? If I close this like I was calling numerator, I have here trefoil, Hopf-link, and then trivial thing. So let's twist it once. So I will have Hopf and all of the other will be trivial. Let's try. And maybe you should have name. When there are three twists, will be D3, D2, D1. When I lost 0, this is D1. And D0 and D infinity. So what I want to say is to make one negative twist. Undo 3 to 2, 2 to 1, 1 to 0, 0 to minus 1. Because then numerator will be Hopf-link. And why Hopf-link? Because we know that Hopf-link is the same as mirror image. So then I will compute for mirror image, and we get nice relation, which say that these coefficients are dependent. So let's do this. Maybe still I will do pictures. So B3, but now we have only two twists. We do one negative twist to undo, plus B2. No, there's only one now. 2 is going to 1, 1 is going to 0, plus 0 is going to negative. And what happened with infinity? We should remember that there will be some twists, so let me write infinity from definition. We started from this, but then we add one negative crossing. But negative crossing is not really negative now. If you think about orientation, I believe that this is positive twist. I'm just checking. So anyway, so now we see. So this is equal to 0. This is our defining relation after twist. And now we close this as numerator. I will close on two sides. On one side is enough. But that's really A. So, what we got? Hopf-link. I will call this for a moment positive Hopf, even if Hopf-link is amphitheral, is the same as mirror image. So we got equation B3 Hopf positive plus B2. This is crossing is, I think, will be positive. But always is good to check. So this will be 2a plus b1, that's trivial component, plus, this is probably negative, yes, a inverse, and this is positive, a inverse b1, 0, plus a b infinity. And maybe this is a trivial component, just to be sure. So this is 0. So from this we can compute Hopf-link, and knowing T and substituting what I was showing before, we have some formula for B positive. But we can do mirror image. Or maybe here we'll just twist one small in negative direction, and in such a way this became half. But I prefer to write again another. We have several rather easy observations, so let's write this other easy observation, which work with arbitral, but let's do it for cubic. What happened for mirror image? What happened for mirror image? So first of all, mirror image is well defined for R3. It's relatively well defined for surface cross interval. However, where to put mirror? Of course, I will put mirror in level f times 1/2. But some product like this, we know, have non-unique decomposition. If the manifold have boundary, we know well that if you take the one which Ria was doing F03 times interval, is the same as torus with 1 whole time interval. It's just hand body of genus 2. Anyway, this is side remark that we should be careful that even for surface cross interval we have mirror image, but it is not always uniquely defined. But we can do much simpler, and this is what we decided to in our paper. Instead of trying to make mirror image of our knot, which may be difficult or impossible, we just change orientation of our manifold and make exactly this calculation. So maybe we should say, and Ria I think was stressing this, that when you draw this picture, we think that in our tree manifold there's a small disk, and in this disk we take orientation of manifold. Manifold was oriented in this disk with orientation. So this makes sense. So we change to mirror image as changing orientation. M, let's call this M with change orientation. And then it's not so difficult in general case and here as well, that what happened with our equation? Just the role of B3 will be taken by B0, the role of B2 by B1. B infinity, because of this twisting, will be slightly different. So this is, you can say, torn. L in M and L in M bar differ by. Of course, we have to do something with basic elements, but assume that we can that we can do something. They differ by, because I wanted for this calculation the changing of B0 to B3, B1 to B2, and A to A inverse, because kind of what was positive twist now in manifold is negative twist, and finally B infinity is going to A, I think, to 3, I think that's to third power B3. So it's convenient to substitute some B, V equal A to 3 over 2 B infinity. I hope I wrote it correctly. So then in our change, B, V is constant. But otherwise it's small change. Anyway, this is just very easy follows from reading this diagram backward, because mirror image is changing the role of positive and negative. But from this we get that for negative we get exactly B0 negative, B2 is going to B1, but A inverse plus B2 T plus A, instead of A inverse, B3 plus, and with this change we get here A squared, B infinity times T equals 0. So now we say that these are equal. So we try to multiply this by B0, this by B3, anyway, eliminate this and get long relation. So this is the first thing, but there's only one relation in our polynomial. This would be still Nice. And for a while, we thought there's just one relation, which we called Hopf relation. But then after more calculation, we found that there's more relations, and we don't control them. So rather it is negative statement that we have more relations than this. So what is the best solution to this? Solution by omitting problems, of course. So let me write how we can omit problems. So how we omit problems? We choosing the link. Instead of this link, we just say that our link is just the Kauffman bracket skein module, cubic, not bracket, is cubic skein module of S3. Maybe I will write as R3. There is some module, but here in R3, like in general surface cross interval, I think Ria was mentioning this, we have natural multiplication, stacking one above another. Here to be even disjoint sum, because stacking one above another, you can make them disjoint. So this is not only module, but this is ring or algebra. So we can take this ring as a ring with which we work. So maybe I finish with one conjecture, which with discussion, namely, what happened with this ring, how it really coordinates with whole skein module. Okay, so let's first remind what was mentioned by Ria, that when we have manifold embedded in other manifold, then this map, called this I, this map is defining homomorphism of skein modules, including homomorphism of cubic skein module. So it is S for infinity of M of N with any fixed ring. Of M. So we have homomorphism. So we call this I star. That's homomorphism. But conjecture which will make our ring very attractive is that this monomorphism in the case of N being disk or R3 is monomorphism. So this is conjecture. For every skein module is open, almost for every skein module is open conjecture. Not only for cubic. Conjecture. This I star going from S3 infinity. Let's write it not R3 but disk, but it's the same. Is monomorphism. Which means that when you compute something in S3, you cannot kill some elements going outside of S3 into manifold. So this conjecture was slightly more studied for the case of Kauffman bracket. And again, to finish almost, I can say that for Kauffman bracket, I was thinking for a long time that Doug Bullock proved this. And now people tell me that he didn't prove, so even for Kauffman bracket it is open. But it is related to, just to finish with story with Paweł again. So why I thought that is done? Because there's the following story. So one day Paweł thought that he can have method of disproving Poincaré conjecture using Kauffman bracket skein module, or maybe other skein modules. And how it more or less worked, that he conjectured that if you have counterexample to Poincaré conjecture, you take some link which cannot be pushed into ball, because this is property of such counterexamples. Then when you try to compute Kauffman bracket, you never finish. Computational tree will be never finished. And this was, I think, proven by Doug Bullock. But whether it was giving monomorphism here, people now telling me that no. I'm not totally convinced, because somehow the main paper of Bullock seems to be not published, only one of them. But anyway, it was not totally idea didn't work, because idea was working as well for contractible, non-compact manifolds. And this is what Ria was mentioning, how we really were dealing with Whitehead manifolds. So for Whitehead manifolds, Paweł conjectural Bullock theorem work, which when you start from some link which cannot be pushed into the ball, resolving tree is infinite. And then you can make more precises in specific Whitehead manifold, this classical one with Jim Hoste, we prove that cannot be reduced. So I think this is very good conjecture, maybe first trying with Kauffman bracket, not with, I wrote 3, it should be 4. But for 3 is open as well. Even for 2 is open. Cubic. So with this conjecture, I think I will stop. Moral is that not much is known. Thank you.
Questions?
Over coffee, maybe.
So, I know that it's possible to get some other knot invariants from the skein relations already for
yes.
Gauss polynomials and so on. Can you get other knot invariants from this?
Yes, but all what we did, except something which really is coming from Jones or Kauffman, because you can use equation, shift it, and you have longer relation. So otherwise we have examples, but they are open, as open problems. That this substitution is giving new polynomial invariant, this substitution is giving new polynomial invariant. But we don't have anything we can prove. Some of them may came from 2K-blink of Jones or 2K-blink of Humphrey polynomial. So still they are not new, but will be different description. In fact, this is partially known. I was just talking to you, yeah. That,
colored, symmetric colored polynomials is what I was saying.
Yeah, but this is K-blink. So yes, this is very good, but it's K-blink. But there were papers which we should study. There was a paper of Wadati Akutsu who claim linear relation. And this is kind of strange story because this paper was not that famous because Jones was saying that this is coming from 2K-blink. So if it's coming from 2K-blink, in this case and other 4K-blink, then it's interesting, but not that interesting. It was before volume conjecture, so maybe now people will say it's very interesting. But yeah. But you have your own, so you promised to send me. So good.
Any other questions? If not, let's thank Józef again. I'll stop recording.